I think we are about to enter the last talk today, given by Professor Li. Professor Li is a professor from Fudan University in Shanghai, and also he's a member of the Chinese Academy of Science, and also fellow of the World Academy of Science, and he won many awards. Well, I think he's more than 5 academicians. Yeah, so he's also the foreign members of French Academy of Science. This is very closely related to France. Today he's going to give a talk on from phenomena of synchronization to boundary synchronization for hyperbolic system. So let's give a warm applause for Professor Li.
So first of all, I'd like to thank the Institute for Advanced Study for the kind invitation and the warm hospitality. At the beginning of my talk today, I will briefly say something about Philippe's great contribution to the China, including Hong Kong, France, scientific cooperation, especially in applied mathematics. In as early as 1982, Philippe made his first visit to China. And afterwards, he has been to China many times in different universities and research institutions. He was nominated honorary professor of Fudan University in 1994 and of Xi'an Jiaotong University in 2006. He is one of the founding members of Institut Sino-Français de Mathématiques Appliquées, created in 1998. His 6 monographs and textbooks has been translated into Chinese with great influence. He is co-editor-in-chief of the series in Contemporary Applied Mathematics, published by Higher Education Press and World Scientific since 2000. He gained the International Scientific and Technological Cooperation Award, confirmed by Shanghai Municipality in 2006. He was elected a foreign member of the Chinese Academy of Sciences in 2009. Due to all the above, he is a reliable friend of Chinese mathematicians and a great ambassador who facilitates exchange and cooperation between China and France in applied mathematics. A conference dedicated to him on the occasion of his 80th birthday was organized in May in Shanghai. Synchronization is a widespread natural phenomenon. Thousands of fireflies may twinkle at the same time. Audiences in the theater can applaud with a rhythmic beat. Pacemaker cells of the heart function simultaneously, and the field crickets give out an unanimous cry. All these are phenomena of synchronization. This morning, 2 speakers have also mentioned its name. In principle, synchronization happens when different individuals possess likeness in nature. That is, they conform essentially to the same governing equation, and meanwhile, the individuals should bear a certain coupled relation. The phenomena of synchronization was first observed by Huygens in 1665. And the research on synchronization from a mathematical point of view, dates back to Wiener in 1950s. The previous studies on this topic focused on systems described by ODEs, such as like this, where f is an n-dimensional vector function independent of I. The right-hand side of this system shows that every capital Xi possesses two basic features, that is, satisfying a fundamental governing equation and bearing a coupled relation among one another. So for any given initial data, if for any given initial data, the solution to the system as t goes to infinity satisfies this condition, namely all states tend to coincide with each other as t goes to infinity, then we say that the system possesses the synchronization in the consensus sense. Or in particular, if the solution satisfies xi goes to constant a as t goes to infinity, where a is a constant state which is a priori unknown, then we say that the system possesses the synchronization in the pinning sense. Obviously, synchronization in the pinning sense implies that in the consensus sense. These kind of synchronizations are all called the asymptotic synchronization, which should be realized on the infinite time interval. What we have been doing in the recent years with Professor Hyperbolic is to extend in both concept and method the universal phenomena of synchronization from finite dimensional dynamical systems to infinite dimensional dynamic systems, the systems of ODE to systems of PDE. It should be the first attempt in this regard, and the earliest relevant paper was published in 2013 in a special issue of Chinese Annals of Mathematics in honor of the scientific heritage of Jacques-Louis Lyons. And the result was also announced in 2012 in compte rendu. We will consider the following coupled system of wave equations with Dirichlet boundary conditions like this, with the initial data where omega is the boundary domain with smooth boundary gamma, gamma 0, and gamma 1. Capital U is the state variable. Capital A is a coupling matrix with constant elements. Capital D, called the boundary control matrix, is an n by n full column rank matrix with constant elements. And capital H stands for the boundary control. For a system governed by PDE, we can similarly consider the asymptotic synchronization as in the case of ODEs. If the answer of the, if we have the positive answer, then this conclusion should be realized spontaneously on an infinite time interval and is the naturally developed result desired by the nature of the system itself. But for a system governed by the PDEs, as there are boundary conditions, another possibility exists, namely to give artificial intervention to the evolution of state variables through appropriate boundary controls, which combines synchronization with control and introduces the study of synchronization to the field of control. This is also a new perspective to the investigation of synchronization for systems of PDEs. The boundary control comes from the boundary condition on gamma 1. The elements in capital H are adjustable boundary controllers. And to put the boundary control matrix capital D before H will provide many possibilities of combining boundary controls. Precisely due to the artificial intervention of control, we can make a higher demand. That is, to meet the requirement of synchronization within a limited time instead of waiting until t goes to infinity. The corresponding question is whether there is a suitable large capital T such that for any given initial data, through proper boundary controls with compact support in the interval 0 capital T, that is, to exert the boundary control at the time t, and abandon the control from the capital time capital T. The solution to the system satisfies all state variables tend to be the same since the time capital T, while U is called the corresponding exact synchronizable state, which is unknown beforehand. If the above is satisfied, we say that the system possesses the exact boundary synchronization. Here, exact means that synchronization of state variables is exact without error, and the so-called boundary indicates the means or method of control, namely to realize the synchronization through boundary controls. In the above definition of synchronization, through boundary controls on the time interval from 0 to capital T will not only demand the synchronization at the moment capital T, but also require synchronization to continue when t is bigger than capital T. That is, after all boundary controls are eliminated. This kind of synchronization is not a short-lived one, but exists once and for all, as is needed in applications. Of course, we always assume that the initial data belongs to this space and the solution to our problem belongs to the corresponding function space, which will not be specified one by one here. We consider X boundary null controllability. The exact boundary synchronization on a finite time interval is closely related to the exact boundary null controllability. If there exists capital T such that for any initial data, through boundary controls with compact support, the solution to the problem satisfies as t bigger than capital T, all components of state variables are all 0, then we say the system possesses the so-called exact boundary null controllability in control theory. This is, of course, a special case of above mentioned exact boundary synchronization. For a single wave equation, the exact boundary null controllability can be proved by the HUM method proposed by Jacques-Louis Lyons. For a capital system of wave equations, since for the purpose of studying the synchronization, the coupling matrix capital A should be an arbitrarily given matrix. The proof of the exact boundary null controllability cannot be simply reduced to the case of a single wave equation. However, using a compact perturbation result, it is possible to establish a corresponding observability inequality for the adjoint system, and then the HUM method can be still applied. So we can obtain the following results. Assume that the number of boundary controls is just equal to the number of the state variables and let the domain satisfy the usual multiple geometric condition. Then, through n boundary controls, when capital D is suitably large, the exact boundary no controllability can surely be realized for all initial data. On contrary, suppose that the number of control is less than n, that is, then no matter how large capital T is, the exact boundary no controllability cannot be achieved for all initial data. In the case of partial lack of boundary controls, which kind of controllability in a weaker sense can be realized by means of fewer boundary controls? This is a significant problem from both theoretical and practical point of view, and can be discussed in many different cases, as will be shown in the sequel. Very meaningful synchronization should exclude the trivial situation of no controllability, and then we have the following results. Assume that the system under consideration is exactly synchronizable, but not exactly no controllable. That is to say, the system is exactly synchronizable with rank capital D less than capital N. Then the coupling matrix A should satisfy the following condition of compatibility, where small a is a constant independent of K, namely the sum of all elements in every row of capital A is the same, so-called low sum condition. Let E1 is a vector like this. This compatibility condition is equivalent that E1 is the eigenvector of capital A corresponding to the eigenvalue A. Let C1 be the corresponding synchronization matrix. C1 is a full low-rank matrix. Obviously, the synchronization requirement can be written as this. C1U is identically equal to 0 as T bigger than capital T. Moreover, the kernel of C1 is just the span of E1, and then this compatibility condition is equivalent to that the kernel of C1 is a one-dimensional invariant subspace of A. So this compatibility condition will be called the condition of C1 compatibility in what follows. It is also equivalent that there exists a unique matrix A1 bar of order n-1 such that this its equation is satisfied. Such a matrix A1 bar is called the reduced matrix of A by C1. Under the condition of C1 compatibility, let W1 equals C1U, then the original system for the variable mu can be reduced to the following self-closed system for the variable W1 with A1 bar instead of A1. Under the condition of C1 compatibility, the exact boundary synchronization of the original system is equivalent to the exact boundary no controllability of the reduced system for W. Then we can get the following results. Assume that the condition of C1 compatibility is satisfied, and the domain omega satisfies the usual multiple geometric condition. Then there exists a quite large capital T such that for any given boundary control matrix with the rank of C1D is equal to n-1, the exact boundary synchronization of our system can be realized at the time capital T. On the contrary, if the rank of this matrix is less than strictly less than n-1, in particular, if rank of D is less than n-1, namely the number of boundary controllers is fewer than n-1, then no matter how large capital T is, exact boundary synchronization can never be achieved for all initial data. The above condition of C1 compatibility is not only sufficient, but also necessary to ensure the exact boundary synchronization, and this condition for the boundary control matrix capital D such as the rank of D and the rank of C1D both are equal to n-1, appropriately chosen n-1 boundary controls suffice to meet requirements. I have to mention that in a study of synchronization for systems governed by ODEs, the low SEM condition is imposed to the system according to physical meanings as a reasonable sufficient condition. However, for our systems by PDE and for the synchronization on a finite time interval, it is actually a necessary condition which makes the theory of synchronization more complete for systems governed by PDE. I just omit this. How will be the situation if the number of boundary controls is further reduced? Then we can only further lower the standard to be reached. One possible way is not to require synchronization of all state variables, but to divide them into several groups, for instance, P groups, and then demand synchronization of state variables within every group, whereby we get the concept of exact boundary synchronization by P groups. So let P be an integer like this, and we rearrange the components of U into P groups. Our system is exactly synchronizable by P groups at time capital T if for any given initial data there exists boundary controls with compact support such that the solution satisfies the following conditions for T bigger than capital T. Here, U1, UP is called the exact synchronizable state by P groups, which is a priori unknown also. Let S be defined in this way and CP be the following full low rank matrix of synchronization by P groups. The exact modular synchronization by P groups is equivalent to ask CPU is identical or equal to 0 when T is bigger than capital T. We can establish all the previous results in a similar way after having overcome some technical difficulties. For instance, if the exact boundary synchronization by P groups can be realized by means of N minus P boundary controls, we can get the corresponding condition of CP compatibility. That is, there exists a unique reduced matrix AP bar such that this quantity is satisfied, which means that the coupling matrix A satisfies also the low sum condition but by blocks. Under the condition of CP compatibility, and the domain satisfies the usual multiple geometrical condition, there exists a suitably large capital T such that for any given boundary control matrix capital D with rank of CPD is equal to M minus P, the exact boundary synchronization by P groups can be realized at the time capital T. On the contrary, if the rank of this matrix is less than n minus p, in particular, if the rank of D is less than n minus p, then no matter how large capital T is, the exact boundary synchronization by P groups can never be achieved for all initial data. So the situation can be listed in this table. So we show the minimum number of boundary controls given in each cases. What can we do when the number of boundary controls that can be chosen further decreases? The aforementioned controllability and the synchronization should both be established in the exact sense. However, from the practical point of view, some minor error will not affect the general situation. So it also makes sense that these requirements are tenable only in the approximate sense. What we are considering here is the situation that no matter how small the error given beforehand is, we can always find suitable boundary controls so that the controllability or synchronization can be realized within the permitted range of accuracy. Since the error can be chosen progressively smaller, this corresponds actually to a limit process, which thus allows the analytical method to be applied more effectively. The corresponding controllability and synchronization are called approximate boundary node controllability and approximate boundary synchronization. We say that our system possesses the approximate boundary node controllability at the moment capital T if for any given initial data there exists a sequence of boundary controls with compact support such that the corresponding sequence of solutions satisfy the following condition. As t goes to as n goes to plus infinity, the solution goes to 0. Obviously, the exact boundary node controllability leads to the approximate boundary node controllability. However, approximate boundary node controllability cannot lead to the exact boundary node controllability in general. In this case, consider the corresponding adjoint problem where A T denotes the transpose of A. For the adjoint problem, we say that it is D observable on the interval 0 capital T if the observation D transpose and the normal derivative capital phi is identical or equal to 0 on the time interval from 0 to capital T on gamma 1 implies that the solution is identical or equal to 0. The de-observability is only a weak observability in the sense of uniqueness, which cannot guarantee the exact boundary node controllability. However, our system is approximately more controllable at the moment capital T. We can prove that if and only if the adjoint system is de-observable on the interval 0 capital T. Therefore, if the number of the boundary controls equal to the number of state variables, then by homogeneous uniqueness theorem, our system is always approximately node controllable by means of n boundary controls, even without the multiple geometrical condition. However, approximate boundary node controllability can be realized even if m is less than capital M, namely by means of fewer boundary controls. To transfer the approximate boundary node controllability of the original system equivalently to the de-observability of the adjoint problem cannot solve specifically the problem of judging whether a system possesses the approximate boundary node controllability, nor is it clear to what extent the weakened concept may reduce the number of boundary controls needed. Assuming that our system is approximately neurocontrollability at the time capital T, then we necessarily have the following enlarged matrix composed of capital A and capital D is full rank. So rank of this enlarged matrix is equal to the number of state variables. This is a necessary condition which helps to conveniently eliminate a set of systems that do not meet the requirements. This condition is nothing but the so-called Kalman's criterion for guaranteeing the exact controllability for the following system of ODEs. However, here we get it from a different point of view. Since this condition is independent of capital T, is not a sufficient condition for the D-observability for adjoint program in general. Otherwise, our D-observability should be realized almost immediately, but it is not the case because of the finite speed of wave propagation. However, we can prove that under certain assumptions on the coupling matrix A, this condition is also sufficient for guaranteeing the approximate boundary neurocontrollability for capital T large enough for some special kinds of systems. For instance, some one space dimensional systems, some 2x2 systems, the cascade system, or more generally, the nilpotent system under the multiple geometrical condition, and so on. For the exact boundary neurocontrollability, as we said before, the number n is the rank of capital T should be equal to capital M, the number of state variable. However, the approximate boundary neurocontrollability could be realized if the number of capital M is substantially small, even if this number is equal to 1. Nevertheless, even if the rank of D might be small, but because of the existence of influence of the coupling matrix A, in order to realize the approximate boundary neurocontrollability, the rank of the enlarged matrix should be still equal to M, the number of state variables. So, the number of N of D is the number of direct boundary controls acting on gamma 1, and the rank of the enlarged matrix denotes the number of total controls. Differently from the exact boundary neurocontrollability, for the approximate boundary neurocontrollability, we should consider not only the number of direct boundary controls, but also the number of total controls. We give an example. We consider this coupling system of wave equations, and the coupling matrix is like this. It's of a cascade type. In particular, if we take capital M is equal to 1 with only one boundary control, small h of t, the boundary control matrix like this. Then the boundary condition on gamma 1 is written as un equal to the control, and the observation for the adjoint problem is the d transpose the moment derivative phi m identically equal to 0. By the result of Alabo, under the multiple geometrical condition, the corresponding adjoint problem is D-observable. Then, original system is approximately neurocontrollable at the moment t. Therefore, by means of only one boundary control, small h, we meet the approximate neurocontrollability. Moreover, we can prove that for any given boundary control matrix such that the corresponding Kalman's criterion is satisfied, similar results hold. Therefore, the Kalman's criterion is sufficient for the coupling system of cascade type. Even only one boundary control can be used to realize the approximate no controllability for our system. However, the choice of such a boundary control cannot be arbitrary. To illustrate this, we take D like this, and the corresponding observation for the adjoint problem is like that, which cannot guarantee the D observability. If situation still holds, even more boundary controls are used. For instance, if we take capital M equal to capital M minus 1, and there are M minus 1 boundary controls, and the boundary control matrix Z like this, then observation of the adjoint problem is like this. So the first M minus 1 normal derivatives are 0 on gamma 1. In this case, we use M minus 1 boundary controls, but they are still useless for the approximate boundary no controllability. The reason is very simple. The Kalman's criterion fails in these cases. We say that our system possesses the approximate boundary synchronization at the moment capital T. If for any given initial data there exists a sequence of boundary controls with compact support such that the sequence of solutions to our problem satisfies as Tn goes to infinity, the difference between two components goes to 0. Obviously, if system is exactly synchronizable, then it must be approximately synchronizable. However, the inverse is not true in general. Moreover, the approximate boundary no controllability obviously leads to the approximate boundary synchronization. We should exclude this trivial situation in advance. Therefore, we assume that the system is approximately synchronizable but not approximately no controllable. Then, as in the case of exact boundary synchronization, the coupling matrix A should satisfy the same condition of C1 compatibility. Setting W1 is equal to capital 1 U, we get again the reduced system and its adjoint problem. We call it the reduced adjoint problem. Similar to the D observability, we say that the reduced adjoint problem is C1D observable on the time interval if C1D transpose times the normal derivative of psi implies the solution psi is identically equal to 0. And under the condition of C1 compatibility, our system approximates synchronizable at the moment capital T if and only if the reduced adjoint problem is C1D observable on the time interval 0 capital T. Under the condition of C1 compatibility, if the rank of this matrix C1D is equal to n minus 1, then our system is always approximately synchronizable even without the multiple geometrical condition. If the rank of this matrix is less than n minus 1, and in particular, if we essentially use fewer than n minus 1 boundary controls, it is still possible to realize the approximate boundary synchronization. As in the case of approximate boundary no controllability, under the condition of C1 compatibility, we have that suppose that system is approximate synchronizable at time t, then we necessarily have the rank of this enlarged matrix is just equal to n minus 1. This condition is not sufficient in general for our requirement. However, it is still sufficient for T large enough for some spatial systems under certain additional assumptions on capital A. We can prove that if system is approximately synchronizable under the action of boundary control matrix capital D, no matter whether the condition of C1 compatibility is satisfied or not, we necessarily have the rank of this enlarged matrix is bigger than or equal to n minus 1. Namely, at least n minus 1 total controllers are needed in order to realize the approximate boundary synchronization of system, our system. Assuming that our system is approximately synchronizable and the minimal rank condition, the rank of this matrix is just equal to n minus 1, then the coupling matrix A should satisfy the condition of C1 compatibility and same algebraic properties, and there exists a scalar function U as the approximated synchronizable state, such as all components of U tends to U as n goes to infinity. Moreover, the approximate synchronizable state is independent of the sequence of the employed controls. Therefore, the original approximate boundary synchronization in the consensus sense reduces to that in the pinning sense. For some special systems of n wave equations, even n is quite large, only one suitable boundary control can be used to realize the approximate boundary synchronization. For instance, we consider this system of two equations, and the coupling matrix like this satisfies the low-sum condition, namely the condition of C1 compatibility, and the reduced matrix is of the cascade type. Moreover, capital D is like this and C1D is like this. Since the reduced system is just of the cascade form, the corresponding Kalman's criterion is not only necessary but also sufficient. Therefore, by means of only one boundary control, we get the approximate boundary synchronization. Okay. When we have the boundary condition on gamma 1 as like this, we have the same result. However, if we take the boundary condition on gamma 1 as like this, or even we take two boundary conditions, the Kalman's criterion fails and the approximate boundary synchronization cannot be realized. So we can discuss the approximate boundary synchronization by P groups in a similar way. So the situation is just like this, and the minimal number of total controllers is like that. Here we just give a system which is approximately boundary synchronizable by two groups, but it's not approximately boundary synchronizable. The system is like this, and we check that this system satisfies the condition of compatibility, C1 compatibility, as well as condition of C2 compatibility. However, can prove that the system is not the approximate boundary synchronization by means of only one control. However, it is approximate boundary synchronization by two groups in this case. By two groups by means of only one boundary control. So we have to consider another kind of synchronization, so-called induced approximate synchronization. That means that we can not always realize the approximate boundary synchronization by P groups under the minimum rank condition. Therefore, we have some hidden information. We have to find some hidden information. And this one can be done just take example. We just take this example, and we have the condition of C2 compatibility, and this system is approximate boundary synchronization by two groups, and we have something like this by definition. However, in this case, the number of total controllers, that means the rank of this enlarged matrix is equal to 3, which is bigger than n minus 2. Then we can get the induced approximate synchronization, which implies the following much precise conclusion. That means U1, U2 goes to U, but U3 and U4 goes to 0 in this case, as n goes to infinity. How many minutes? The time is over or not? Okay. So same prospect for the future. I think it's I have no time to say. But finally, on this grand occasion, please allow me to extend my best wishes to Philippe. May good health, happiness, and success be with you always. I also hope that the friendship between us and between mathematicians in China, including Hong Kong, and France, can last forever. Thank you very much.
Okay, now we have time for Q&A. Okay, yes.
Thank you. Thank you very much for your kind words. I have a question of very simple. Where do you use the linearity of the equations? Could you have some kind of mild nonlinearity with respect to U, or is it restricted to linear PDEs?
Yes,
Your approach.
this is something I want. Our research is limited to the linear situation, and the method employed is also linear. However, the study of synchronization should be extended to the nonlinear situation. At present, in the one space dimensional case, for the coupled system of quasi-linear wave equations with various boundary controls, the exact boundary synchronization has been achieved in the framework of classical solutions. And there is still larger developing space for more general research. And this for higher dimensional case, just in a very weak sense, the solution. Mm-hmm. So it's difficult to do the nonlinear research.
Thank you.
Thank you. Any other question? How about the chairman from mathematics department, Professor? And
In fact, two questions. One question is usually how big is the capital T? How to estimate? Some of your film says for sufficient large capital T, right?
Yeah.
So how large is this T usually?
This is one question. And the second
And the second question is, you mentioned the one-dimensional quasi-linear system.
Yeah.
So if you have short wave, then can you still control?
Okay. But to estimate the controllability or synchronization time, capital T, is a complicated problem because we have the coupling matrix, capital A. Not only one equation, one wave equation is easy to know the speed of wave, and we can get the precise estimation. But here is a coupling matrix, so we have to suppose that the capital T is quite large. But for some precise system, we can do the precise estimate. And also for the one space dimensional case, we just consider classical solution, the framework of classical solutions. So it's very smooth, and we use fixed point theorem to get the result.
Thank you. And any other question from? No. Yeah. Yes, please.
So I would like to ask about all this kind of estimation. So how does it help for mechanical engineering? They are very important in control and dynamics. So how does this kind of estimation system helps their problems?
So we would like to know the real situation for the
The applications.
the application that we can do something for the special situations. But for the moment, this is just theoretical consideration. So
I see.
the practical problem may be nonlinear, and more complicated. But the linear situation we have studied is just a beginning, yes.
I
We
see.
should find more examples from practice.
Yeah, because it's a bit visualized with all this equation. Normally, like talk about oscillation, there's some kind of wave graph, but it's very hard to visualize when all this equation. But yeah, so that's why I'm asking this question. Yeah.
Okay, thank you.
You see, Thomas is only the junior year undergrad student. Yeah, so he's IS fan. He attend every lectures of IS.
Okay.
Yeah, never miss it. So always ask 1 to 3 question. So, true. Yeah. Any other question from PhD student? Yeah. Yes, please. Yeah.
So, we'll talk about the hyperbolic system. And for example, from Navier-Stokes to Euler, so you have different boundary conditions.
Yeah.
In that case, do you have any study of this kind of things?
Yes.
For example, for your hyperbolic systems, if you add a viscosity or something.
Yeah. Here I have a question like this. So we hope to consider this kind of problem for more coupled systems of either linear or nonlinear equations, including the beam equations, Pratt equations, and elasticity equations, and so on.
Yeah.
So this is just the beginning.
I see. So for example, suppose you linearize the Navier-Stokes linear around a constant state or something, we'll consider the linearized system. Then, because in that case, it's a hyperbolic coupled with parabolic.
Not only hyperbolic. This is something parabolic.
Yeah. So that's
There should be a very interesting questions in the future. I think not only for hyperbolic system, but also
coupled with parabolic
for
stuffs. Yeah.
Parabolic and coupled hyperbolic parabolic systems together.
Yeah.
Yes, it's a very interesting question. Even in the nonlinear case.
Yeah.
Yeah.
Okay. Yeah. Thank you.
Thank you. Any other question? If no, then we give thanks to Professor Lee again. Yeah, thank you.